Morning, everyone. My name is Scott Poole. I'm a Director of Engineering for AirBorn. AirBorn is really the pedigree, as we mostly know AirBorn for in this room, is the design and manufacturing of interconnects. But what's really interesting is, and a lot of folks don't know, AirBorn's actually been in the power systems business for 30 plus years, design and manufacturing for mil-aero, defense, ground vehicles. And our designs have varied from 50 watts up to upwards of 300 kilowatts for flight applications. And we're a very vertically integrated company. So, as we're going through this, I know there's going to be a lot of questions as to why are we talking about power electronics from a interconnect company. One of the primary pushes for this presentation is in those 30 years, and I've been personally involved for 20, as we've designed the power electronics, and I know we've seen some presentations this morning about the consumption of power, but it's what happens in the earlier stages during the design and development, and the challenges, and the heartburn, and really the logistics of our presentation is some of the things that VITA don't necessarily require or aren't very tightly controlled, and how this really ties in on the VITA aspect. But this isn't just a VITA issue, this is a power electronics issue, period. We have 5 things that we've identified that as we've gone through and design development of a lot of different systems in 30 years, the things that have really kept us awake at night and have caused us dramatic schedule slips and have made us go back to our senior management teams and pleaded for more qualification money to respin circuit boards and go back through qualification testing. And some of those really deal with, for example, the high-speed power engines or the high-efficiency power engines. And so when we have gone through this design and development, dealing with lower efficiency components, and we'll go through some examples, how when we started on a journey to really understand this as well as design and develop product to optimize these parameters, this was really at the forefront. Low noise switching, developing systems with clean conducted emissions for ease of integration, ultra clean output voltages. So in this case, VITA does have requirements. VITA 62 requires, for example, 1% on a 12 volt output. Is that good enough? Well, some customers say yes, some say no. So the answer is, it depends. Then ultimately, there's limitations at a system level, card level. And how do we achieve the higher power levels? Well, we have to stack more in parallel. So when we do that, or when any of us do that, there's a lot of inherent problems with communication, sharing, and how do we get past those issues? So the first step I want to talk about, and one of the most important, is the high efficiency power engines. And so we see in the marketplace today, if you pull open a module as an example, a commercially available module, it's not uncommon to see something at a module level 82 to 90%. Okay, sounds reasonable, I guess. And when you integrate that into a system, you have copper losses, you have connector losses, you have wiring losses, filter losses. So before we know it, we're well below 80% in a lot of cases. But thinking positively, and for the purpose of this presentation in round numbers, we'll use a 90% efficiency in this example. And so if we look at a VITA 62 card that's maybe 1,000 watts, 90% efficient, we'd say that sounds pretty good at the surface. In reality, we have about 100 watts to dissipate. And so when we look at what's available in the VITA space as an example, we start to see that we don't see too much above 1,000 watts. There are a lot of exceptions. because we have this 100 watts to dissipate. As we go higher, 1,500 watts, round numbers, 150 watts of power dissipation, all the way up to 2,000 watts, all of a sudden we have 200 watts to dissipate. It's a lot of power. But if we could achieve, say, a 95% efficiency, that same 100 watts of power dissipation that we had at 1,000 watts of output would get us to 2,000 watts of output. So if we kind of look at it backwards and really focus on if we can dissipate a certain amount of power and really focus on the efficiency of our power engines, what does that do for us? In this case, we can see we can essentially double our power output with the same amount of watts lost out of our power engine. So from a thermal management standpoint, that's a win, right? I think everybody would agree with that. These are the technologies, and we'll go into some plots here in a bit, that has been a desire, and it really has become a reality, and it needs to become a reality in pushing those boundaries of efficiencies. When we look at low noise switching, so as we know, we obviously want our power engine to be as quiet and as clean as possible. It impacts us from a conducted emission standpoint. It impacts us from an output voltage standpoint and what we're powering. We want it to be clean. We want it to be efficient. So there's really two main approaches that we see in the market space. We see a modular approach. So there's COTS modules that can be put on circuit boards. Front end filter can be put in place. Possibly a secondary filter can be put in place. And yeah, we can achieve the requirements a lot of times. May not be practical. Again, we have a lot of losses with all the stages. And from a performance standpoint, once you go into a modular solution, there's not a lot of availability into the internals of that engine. So we have just a handful of phenomena up here that can't be corrected because there's no access into the module itself. For example, ringing due to loop inductance. There's a lot of inductance inherent to the module and the leads, the traces, circuit board inside the module. And it just comes down to laws of physics. So really the big push has been, well, how do we move past that and how do we optimize that? The approach has been really in a discrete side, in the discrete technologies. And it's really been driven by a lot with the transistor technologies and some of the micro miniature components that are now available. So in a discrete approach, the filter and bypass components can be located very, very near the switches, which is ultimately desirable. Especially as switching frequencies increase, we get into the hundreds of kilohertz. And it really pushes the technology and the responsibility back to the OEM. So the OEM becomes more responsible for providing a solution rather than, here's a module, go figure out how to integrate this. If you fail EMI, good luck, we'll give you maybe a few recommendations. So by going to discrete, the OEM also has the option to eliminate the leads, as we talked about. Very high inductance cause performance problems, ringing, et cetera. 20 years ago, wire bonds was the greatest thing ever. But that requires special circuit board materials, and a PEG is an example. Wire bonds in general can be problematic to get them scrubbed on properly. And we also have an issue with inductance because the wire bonds are just that, they're wire. So by going to a discrete solution, possibly look at a flip chip, eliminates all of these problems that we see in the noise spectrums. And so if you do everything correctly, you end up with a waveform that looks like such. And so this is an example of a scope probe on a drain source node right at the switch. And we can see there's actually a lot of things that are happening on this plot that I'm not going to go into the engineering details on. But if you were to look up a textbook plot, you would see something very, very similar to this. And this is a real world example. So very little overshoot, very little undershoot, very little ringing. Everything is very critically damped. And ultimately, what that means for the response is, if we look at these plots, our top plot with the yellow line is the 12-volt output on a Vita62 platform. The yellow is the AC coupled 12-volt output. So we can see ripple, noise, regulation. And the bottom is the current. And we can actually, in this case, we ramp the current from 0 to 130 amps over the course of the fastest we could get it without using a hard switch was about 3 to 4 milliseconds. And we can see when we turn the current on very rapidly. For example, in a radar application, we have a really nice output. Very little regulation, degradation, very little ringing, etc. So that's why point number 2, the low noise switching, why that's really important. We've spent the last several years going into these types of technologies. And we're moving into section 3, which is our conducted emissions. So if we have a really clean switching power plant, what we want to do is utilize that to reduce our conducted emissions. And conducted emissions, for anyone who doesn't know, is it's the energy that is coupled back the power line that is produced within our box. So it's the energy conducted back the input. And there are very specific plots. And for the purpose of this, we'll look at a plot on the next slide, which is the CE 102 out of the mill standard 461, which is very common. But most modern day systems, especially if we look at a chassis as an example, require expensive, large volume, very power hungry passive filters to achieve EMI compliance. It's not uncommon. We've seen chassis vendors spend $5,000, $6,000 on an EMI filter. 8 to 10 pounds of weight, so it's an incredible hit in payload. It's an incredible hit in heat. It's an incredible hit in budget. So looking at all the aspects of design development and what is on our wish list, well, the third bullet was, can something be designed to be able to push the EMI requirements back onto the power electronics manufacturer, OEM? And it's kind of a novel concept. It's really not very common in the marketplace. So we took that as a challenge, and the output through a lot of design, a lot of iteration, and really where the market needs to focus is in a plot like this. So if anybody's familiar with CE 102, that's gone through CE 102, we know that it's a very aggravating test. It's very difficult, it's painful, it's expensive. The mill standard 461 batteries of tests are generally 10 days or so. Can range $25,000, $30,000 every time we go for test. So if you have a solution that all of a sudden you feel very confident is going to pass CE 102, you have a greater than a 90% chance of passing all the 461 elements. In this case here, it's a 270 volt input system, 12 volt, 160 amps out, 3.3, 30 amps out. So we're switching quite a bit of power in terms of a couple kilowatts. And there's an AC version that will have similar characteristics as well. But really the big takeaway here is this was with no external filter. This was in a chassis with load cards, no external filter, able to pass CE 102. So again, it was phenomenal achievement, and really where the industry is really pushing forward to. And along those lines, ultra clean power output. So as we mentioned, as an example, VITA 62 does have requirements for noise and ripple. Looking at the 12 volt, it's a 1%, it's 120 millivolts. Anybody who's ever worked with commercially off-the-shelf modules know that if you just take a module, throw it on a bench, a 12 volt module, you might see 400 millivolts. And just to get down to 120 takes a phenomenal effort. If things are really designed optimally, you shouldn't need secondary pulse filter coming out of your output of your power engine for the most demanding applications. And I know there's a lot of folks here, microcontrollers, PICs, DSPs, and either at the power supply level or on the input of the peripherals, there's a requirement to take that 120 millivolts, a lot of applications, and reduce it to 50, 30, 25, et cetera. When we developed the power engine and we were going through the benchmarks, we actually had to get a special TPR 1000 probe from Tektronix. We were not able to measure the noise and ripple. It was down in the noise floor. So this is just an example. Peak-to-peak noise, it swings about 10 millivolts high and about 5 millivolts low, so about 15 millivolts peak-to-peak. And again, that's with no secondary filtering. So for the most demanding application, the requirement's 120 millivolts to be able to achieve 15 millivolts out of a system. I think you'll agree that it's really ripe for the most demanding applications. And the last struggle that we've had has been, okay, so if you have a card that is capable of 2,000 watts and you're, say, in a VITA 62 chassis, customer needs 6,000, we just stack 3 cards in there. Well, a lot of customers or OEMs would say, well, it depends. And again, you'll hear this term, it depends a lot. So if you have a chassis, there's a lot of assumptions that are being made that have to be made until there's characterization done. So in a chassis, you're going to have hot spots, cooled spots, depends if it's liquid cooled, it depends if it's conduction, convection. I mean, there's a lot of variables. And so assuming it's a convection cooled chassis, you're going to have hot spots, cooled spots, there's going to be turbulence, which cause more cooling in certain locations. There's going to be impingement, which speed up airflow. There's going to be dead spots in front of the fan hub. And so all these things, when you put cards in there, now all of a sudden you have one that's running really hot, and then they start not droop sharing properly. And there's not a lot of intelligence typically behind parallelization and sharing. And so when we set off on this journey and is where the technology is going, is there's intelligence that AirBorn has pushed into these cards and the technologies to be able to really allow optimization, if you will, that the cards have the ability to either balance on equal load, if we can balance on thermal response. So if we have a dead spot and maybe one card's running 10 degrees warmer, we can reduce the amount of contribution onto that middle card so that we balance on all cards equally. And so each of the thermal responses will be, within a degree, as an example. They can be set just so they supply equal voltage. And the communication has been a problem in the past with other OEMs also, with the fact that they're trying to digitally communicate, and there's always glitches and lags and loss of comm. We've moved to a CAN bus type communication. The really cool thing and the advantage with CAN bus is, it's been around, automotive's been using it forever. And we can have multiple systems around an aircraft. And if it's, for example, longer than what we want to communicate with over copper, we can use optical product. And really have ultimate control over exactly how everything is contributing and sharing around the aircraft, the ground vehicle, et cetera. And then the N+1 configuration. And then one of the other questions we get asked a lot is, in the paralleling schemes, how many can we parallel? And the answer is, we don't know. We've not found that limit yet. But as what we can tell you is, once you start stacking a lot of cards in parallel, the copper thickness on your backplane, if it's a Vita product as an example, gets tremendously large, right? So 160, 180 amp, 12 volt card, you stack 10 of those, it's 1,800 amps. You better have a lot of copper. Good luck manufacturing that. So at the end of the day, very versatile. And just the summary of features and benefits, just kind of tie everything back together. So in the high efficiency power engines, why is that important? Well, to increase the output with more manageable thermal management and higher reliability. And it's interesting, we just had a major customer come to us with a requirement for liquid cooled cover on a Vita 62 platform. At 90%, they would need liquid cooling. At 95%, conduction cooling. And it's because we can get the power out and we have minimal waste heat at the power levels that our customer requires at 95% efficiency. So with a low noise open architecture switching, we can spread the EMI out, pretty much wherever there's an issue. So if we're driving a load that is causing a non-compliance in EMI spectrum and a customer says, well, maybe at 170 kilohertz, we're failing, we can actually move that energy around in the spectrum dynamically. As we mentioned, conducted emissions, no external filter required. Again, from a swap C standpoint, that's huge. From a schedule standpoint, that's huge. The probability of passing EMI the first time is greatly accelerated. So that's probably really the most important aspect up here. And then the ultra clean output. So again, the supplies are very capable of driving really the most demanding load, most noise sensitive load, and then the sharing and paralleling of the cards themselves.